So this talk is called Understanding IBIS-AMI Simulations. And what we're going to do here is we're going to start out by reviewing some of the fundamental assumptions and terminology behind IBIS-AMI. We'll take a look at how models are put together, the different stages of a simulation and the types of simulations that we can run, and then look at the different classes of algorithmic model and how they affect simulation flows. Along the way, we'll talk a little bit about what we mean by static and dynamic equalization. And when we look through simulation flows, we'll see that different combinations of models have different relativity. So we're going to talk about how to interpret simulation results, and then briefly look at clock processing and how jitter is handled in simulation before summarizing. So first and foremost, as within any engineering process, when we look at IBIS-AMI, it's important to understand what the fundamental assumptions behind all of the analysis are. And IBIS-AMI is built on a fundamental assumption that with a high-speed serial link, we have nodes at the transmitter and the receiver end that we can think of as high impedance nodes, where we have a partition between something we think of as signal processing and something we think of as circuit simulation. And in particular, what we see is that in the transmitter, we believe that there's a signal conditioning function that drives an output driver that connects to the channel electrically, and the connection between signal processing and the channel occurs through a high impedance node. And then in the receiver, once we come into the termination network and through the input buffer, there's a similar high impedance connection to all of the equalization and clock recovery circuitry in the receiver. And what we assume in IBIS-AMI is that the transmitter, the channel, and the receiver's termination network are all designed to operate as a linear and time invariant system and can be assumed to be such. So when we look at an end-to-end channel with IBIS-AMI, there are a number of terms that apply. If we talk about all of the passive, unpowered interconnect, including the transmitter and receiver packages, so sort of everything that occurs from die to die but is not connected to a power supply, we call that the passive channel. Once we bring the transmitter's output and the receiver's termination network into it, we call that the analog channel, and that is the portion of this overall end-to-end link that we're assuming is linear and time invariant and will behave that way. And then finally, once we sort of zoom out to the thing that we really care about, which is everything from the transmitter to the receiver, we call that the end-to-end channel. And what happens here is that we're going to use different techniques to look at the analog channel and the end-to-end channel. The analog channel is going to be analyzed through circuit simulation techniques, sort of what we think about as conventional voltage and current analysis, whether it's time domain or frequency domain. But the end-to-end channel is going to be analyzed using signal processing techniques. So if we look at an IBIS-AMI model, we see three fundamental pieces. There's the analog model, which is describing, in the case of the transmitter, the output buffer and its power supply and its output impedance and its capacitance and things like that. And that is described in the IBIS file associated with the component, and it's the legacy sort of constructs in IBIS that we normally think about. And again, it's assumed to be linear and time invariant. There's an algorithmic model that gets paired with it and is written in such a way that it's designed to be run together with that analog model. And there's a new keyword in the IBIS-AMI inside the IBIS file that points to that algorithmic model and everything that goes with it. And then finally, there's the package model, because at these speeds, the packages have a significant effect on how the signal behaves. And so we have the on-die behavior between analog and algorithmic, and then we have the package model, which can be described directly in the IBIS file, although the constructs there are somewhat limited. So typically that is supplied separately as an S parameter file. When we go to analyze an end-to-end link in IBIS-AMI, we've got a simple link here with a transmitter and its package and a single S parameter block representing a channel and then a receiver. And we go to analyze that. The first thing that's going to happen is that we're going to take the portion of that which is assumed to be linear and time invariant, which is the analog channel, and we're going to analyze that through a process called network characterization using circuit simulation techniques. And then once we get the output of that first stage, which is an impulse response, we're going to take that impulse response as input to the second stage of the analysis, which is looking at the behavior of the end-to-end channel. And at that point, we're either running a statistical or a time domain simulation to find out what the behavior of the end-to-end network is. But the point that we want to make here is that network characterization or circuit simulation is used to derive an impulse response for the analog network, and then that impulse response is what is input to the channel simulation process. So if we take a closer look at that first step of network characterization, and we look at what's going into the simulator, what's going into the process, and what's coming out of it, what's fed into the simulator is the analog portions of the IBIS files, so the analog models, and then literally the user's schematic. So anything that they've drawn and connected, those are going into the simulator. The goal is to find an impulse response for the analog network that has a fixed time step and has been run long enough to let all of the inter-symbol interference or all of the ringing die out. And the method that the simulator uses to do that analysis, to really put everything together and derive the impulse response, is not specified by IBIS. And in fact, some tools use time domain techniques, some tools use frequency domain techniques. Doesn't matter. What matters is that they're capable of producing an impulse response with the proper formatting requirements of a fixed time step and running it long enough out in time so that all the ringing is dying out. Now, I touched on a point earlier, but I want to go back and talk about it again, and that is that when we talk about network characterization, the only thing that goes forward from that point is the impulse response of the analog channel. And so, you know, it seems obvious, but it probably takes a while to sink in, and that is that if the impulse response that's being produced during network characterization is bad, then running channel simulation is a waste of time. Now, the reality is we all do it. The reality is that we all see impulse responses that are somewhat suspect, and then we go ahead and we run channel simulation just to see what happens, and that's totally okay. But it's important to understand that if the impulse response that's produced is bad from network characterization, then everything that follows is suspect. And if you get down the line, if you have an impulse response that was somewhat suspect, and you go down and you're looking at results from channel simulation and they look wacky, well, you know, you knew you were running with bad data. And so, you know, from a personal point of view, what I always try to do is verify the impulse response that comes out of network characterization in some way before I go off and run channel analysis. Now, as it happens, impulse responses are sort of a mathematical abstraction. They're hard to understand for most people. If you integrate them with respect to time, what you get is a step response, and the step response has a lot more correlation to physical reality. So I can look at a step response for a network, and I can look at the voltage levels and the rise time and the delay of the network, and I can bring that back to a lot of the parameters of the network that I'm trying to simulate in the first place and say, do I believe it? Is it right or is it wrong? You can look at either. I just offer this as a thought that if you have trouble looking at impulse response data and you have the option to look at it as a step response, it's often a lot easier in terms of looking at something and figuring out if it's working correctly. The one important thing I want to point out here is that this impulse response for the analog channel does not include any transmitter-receiver equalization. So when you're looking at that step response, you have to keep in mind that all of the TX and RXEQ has not come into play yet. Once we get out of network characterization, we get into the simulation or channel analysis part of this process. There are two types of simulation that we can run. We can run a statistical simulation, or we can run a time domain simulation. And they both have a similar goal in the sense that they predict the behavior of the end-to-end channel, and they produce things like eye diagrams, but they use fundamentally different techniques and they make different assumptions to get there. So in the case of a statistical simulation, what's being input to the process is the impulse response from network characterization, and then the algorithmic models that are part of the AMI models, and then the user's settings for any equalization or any parameters that are being fed into the models, because a lot of these models come with controls, and the user can set the state of the controls. I want this, that, or the other equalization, or I want to turn the DFE on or off. And those are choices that the user makes when they're setting up the simulation that get fed into the simulation models at runtime. What most statistical engines do is they start with a pulse response, an equalized pulse response for the network to be analyzed, and then they feed it into a convolution process. They sort of wrap it back on itself. They make the assumption that data is unencoded and random, and then that what they do based on that single pulse response that gets input is they produce an eye diagram that shows, what the end-to-end behavior of the network is with a fair degree of detail and probability. Now, one of the interesting things that happens here is that IBIS-AMI is a modeling specification, and the tools that we use are simulators. So IBIS-AMI is really specifying the contract between the simulation model and the simulator, what goes into the model, what comes out of the model, but not necessarily what the simulator does with that data. So the outputs that are produced from an IBIS-AMI simulation are not part of IBIS, and consequently they're not guaranteed to be the same across different simulation tools. However, typically they include things like eye diagrams, measurements of eye height and eye width at some probability level, eye contours, and things like that. Now, alternatively, we can run a more detailed analysis called a time domain simulation, or sometimes people call this a bit-by-bit analysis. And so what's input to that is the impulse response, or basically one or more of the impulse responses from the prior steps. Now when we run a time domain, because we're looking at the network's response to a specific stimulus pattern, there's a stimulus that's been defined, and it might be a default, but the user certainly had the chance to modify it. And then the algorithmic models themselves are being run in a waveform processing mode. And what's happening here, as we'll see later on, is that the simulator is using a mixture of waveform processing, or looking at how the models behave on a bit-by-bit basis, or doing convolution in place of the models, depending on the capabilities of the models that are involved in the simulation. And again, the simulations or the responses that come out of the simulation process are, to a large degree, essentially the same as what we had in statistical. In other words, we still have the same fundamental goal of predicting how the network behaves, and we want to see eye diagrams and all the other same things, the eye height and eye width measurements at particular probability levels. But now what will happen is that because we've done a more detailed analysis and we're looking at the network's behavior on a bit-by-bit basis, there may be additional information available. So a big piece of what happens in IBIS-AMI now is we have these algorithmic models that get linked into the simulator at runtime, and the simulator is capable of passing data to these models and pulling data back, whether it be an impulse response or whether it be bit-by-bit waveform data. And it turns out that there are three possible types of algorithmic models that can exist. Now, any individual algorithmic model has an AMI file that comes with it. It's a text file that describes the model's capabilities, and it also describes things like the control inputs that the user can specify into the model. And that AMI file gets broken into two pieces. There's a top part called reserved parameters that are parameters or control functions that are defined as part of the IBIS-AMI specification that have predetermined names and meanings. And so therefore they're part of the spec. And then there's a model-specific part of the file that has all of the individual control parameters that that particular model responds to. What we're interested at this moment is the reserved parameter part of the file, because there are two parameters in particular, init returns impulse and Getwave-exist, that tells the simulator what types of simulation processing this individual model supports. Now, the first type of a model is a model that we talk about as an impulse response or init-only model. And so this is a model that only knows how to process impulse response data. You give it an impulse response in, it adds its equalization, it gives you a modified impulse response back. And that's all that that algorithmic model knows how to do. So if you were to look at the AMI file and the value of init returns impulse was true, the value of getWave exists was false, that's an example of a model that only knows how to process impulse responses. Now, the converse is the model that only knows how to process bit-by-bit waveform data. And so in that case, if we looked at the model's AMI file, and it returns impulse is false because the model doesn't know how to process impulse response data, but getWave exists is true because it knows how to process waveform data. And you can have a third type of model that knows how to do both, where the state of both variables is said to be true. And so what we find is now we have three types of models. Models that only do impulse responses, models that only do bit-by-bit data, or models that do both. And the assumption is that when a model does both, the goal is through either the impulse response or the waveform method for the model to really produce as close to the same behavior as is possible. So another way to look at this perhaps is to think about impulse response processing and waveform processing as a static or a dynamic equalization problem. When we have a model that only processes an impulse response, what we do is we give it an impulse response to the channel, it adds its equalization, and it gives us back a modified impulse response. So it's something that only happens once. In a statistical simulation, there is no bit pattern. Okay, there's only a pulse that gets put through a convolution engine, and an eye diagram gets produced from that. And so consequently, the equalization only happens once. There's nothing that happens on a bit-by-bit basis. And that's where we start talking about equalization being treated as linear and time invariant, because we're assuming that something is happening the same on every bit in the analysis. Now, the interesting thing is that we can have a model that does static equalization, and we can still use that equalization to generate either a statistical or a time domain result. In other words, a bit-by-bit result in the time domain simulator. And we'll talk about that in a little bit. But the idea at the point of this slide is just to say that when we're talking about init or impulse response-based equalization, we're talking about equalization that is essentially static because it's always the same from the beginning to the end of the simulation. Whereas when we're talking about models that are processing waveform data in the getWave call, now we're talking about a model that can vary its behavior on a bit-by-bit basis, either because of something that's going in the model or just because of the variations in the stimulus coming in, which is ultimately how a lot of real hardware works. Certainly DFEs and clock recovery loops work that way. And so when we talk about a dynamic model or a waveform processing-based model, we talk about things like adaptation, we talk about equalization varying on a bit-by-bit basis, we talk about clock recovery behavior, and first and second order CDRs and all those types of things. Those models can only be used to generate time domain results because, in fact, time domain analysis is the only analysis that actually has a stimulus, right? When we talk about statistical analysis, remember there was only a pulse response that really went into the statistical engine, and so consequently there was no stimulus. When we're talking about a model that's varying its behavior in response to the input pattern, we have to use a mode of simulation that actually has a stimulus for the model to respond to, and that's time domain. So what we can do is we can sort of look at these three model types, the Init-only, the Getwave-only, and the dual, and we can talk about the type of equalization that they provide. Where an Init-only model only gives static equalization, a Getwave-only model only gives dynamic, and the dual model does both. So it's really only the dual model where we can meaningfully talk about comparing the behavior of the same model in these two modes to see if we get analogous behavior. So now what happens is that when we go to run a simulation, the simulator has a transmit model and it has a receive model in the same channel. And there's no guarantee that these two models will be of the same type. If one's init only, there's no guarantee that the other one will be the same. And so consequently, what the simulator has to do is it has to look at the mix of the models that are involved. And we just talked about the fact that an individual model can be any one of three cases. So if we have a TX and an RX, 3 times 3 is 9, and there are 9 unique cases or combinations of transmit and receive model that the simulator can be required to handle. And if you've ever heard anything about AMI with reference flows or simulation cases or anything like that, this is where that's coming from. We're talking about the 9 unique combinations of transmit and receive model capabilities. And what we've done here is we've just gone through and sort of enumerated it with the state of each of those 2 variables in the AMI file, the meaning of the model, whether it's init or getwave or dual. And we've given each of those combinations a case number because ultimately if you look into the specification, you start looking at the documentation, we'll be referring to those individual cases. So I want to introduce some terminology here. I'm not going to spend a lot of time on it just because we don't have that time. But whenever we start talking about a simulation flow and we talk about a result, we need to be able to talk about the specific components that went into it, whether it's the analog channel impulse response or the unit pulse or the bit stream. There were 2 forms of equalization. There's impulse response processing, which is defined as like HTE or HRE of T, which is something that we can convolve with other equalization and other impulse responses to generate an equation. And then when we start talking about waveform data processing, we need to talk about really something more like a function call, right? Where we pass a bit stream in, we get a modified bit stream back, and so we have a terminology for that as well. So what we're going to do here is we're going to walk through a couple of these cases. We're not going to walk through all of them, and talk a little bit about what does the simulator do in each specific case to produce the results from statistical and time domain simulation. All right, and we'll refer to them by case number, and we'll talk about the capability of the transmit and the receive model. So the simplest one that we can talk about is case 1, where the transmitter and the receiver are both models that only do impulse response processing. Now, the good news is that when we run a statistical simulation, because they both process impulse responses, we're going to get an output that includes both TX and RX equalization. And really what happens is that we start with the impulse response for the analog channel. The simulator passes it to the transmitter model that adds its equalization. It then passes that to the receiver model that adds its impulse response equalization. So now we have an impulse response that has both TX and RX equalization in it. It convolves that with a pulse because now it gets the equalized pulse response, and it puts that into a statistical engine and post-processes it. And lo and behold, we have a statistical result that includes equalization. The rub occurs when we go to do time domain processing because neither of these models knows how to do any bit-by-bit processing. So when we're going to go now and combine this with a bit pattern, the models don't know how to process a bit pattern. And the solution here is actually pretty simple. It's just that instead of combining that equalized impulse response with a pulse, it just convolves it with a bit stream and generates the waveform data itself. And then what happens is that whenever we're looking at an eye and we're trying to present it, somebody has to make decisions about where the left edge of the eye is and how to present it. That's the function of clock recovery. And since we don't have any clock recovery being performed by the model in this case, that's all being done by the simulator. Now, if we think about what that means, well, it means a couple of things. It means that the equalization that occurs during statistical and time domain simulation is exactly the same, right? Because all the model knows how to do is impulse response processing. It also means that there's really not much reason to run a time domain simulation. You're not going to learn anything new, right? Because there's no unique behavior in time domain unless you're using a data pattern like a low density, like 8B10B, that violates the assumption of random data used in a statistical simulation, or you have some really good reason to look at the network's behavior to a specific stimulus pattern. It also means, by the way, that when you run time domain, because you don't have these big RX control loops that sometimes can take 500,000 bits to settle, we may not have to go run 1,000,000 bits or 10 million bits because we're not learning anything by running more patterns through the simulator. So now let's look at the next case, which is one where the transmitter model is only doing impulse response processing and the receiver model is only doing waveform processing. Okay, and this is a pretty common case. For a long time, people believed that if you had a DFE, you could only have a waveform processing model. And so as a result, this is pretty common. Transmitters tended to be Init-only, receivers tended to be Getwave-only, and this particular case happened a lot. Now, the simulation flow used for statistical analysis is going to be exactly the same. The simulator takes the analog channel impulse response, gives it to the transmitter model, gives it to the receiver model, which doesn't do anything with it because it doesn't know how to process an impulse response. It convolves that output with a pulse. It goes and it then puts it into the engine, post-processes it, and generates an eye diagram. But the rub is that because there's no RX equalization involved, because the model doesn't know how to process an impulse response, what we have is a result that does not include receive equalization, which is why these things are in red. When we go to the time domain, well, now what we've got is we're introducing dynamic equalization in the RX because we're doing bit-by-bit processing. And so what happens is that we have the impulse response that has the transmit equalization in it coming out of this same process as we had on the left. We convolve that with the bit stream, and what that does is that effectively generates the waveform that you can think of as being the input to the receiver model. It's the waveform for however many bits that shows what's happening at the receiver die pad as it's being fed into the receiver equalization and clock recovery circuitry. We generate that waveform, which is here. We feed it into the waveform processing portion of the receiver model, and then what comes out is a waveform and clock tick data that we can put into the simulator and generate eye diagrams and all these other results from. And that's now with the result of having static, one-time only transmit equalization, but dynamic bit-by-bit receiver equalization. What are the implications? Well, if we look at the statistical simulation results, you sort of have to think of them as being at the receiver die pad because there's no receiver equalization there. Or maybe you don't look at them at all, but the fact is you have to think of them as missing something. The transmitter behavior is exactly the same in statistical and time domain because it's a one-time only model. And when we're running our time domain simulations, however long it takes all of the feedback loops in the receiver model to settle, well, that's how long we have to wait before we can start accumulating things like eye margins and eye opening data. And then finally, let's look at case 9. This is the case where both models support both impulse response and waveform processing data. So the statistical flow looks exactly the same as case 1, right? We just pass the impulse down and get transmit receive equalization in it. The time domain flow is interesting here because what happens is that we do the processing of the impulse response just as we did before, and then really we don't do anything with it. We take the bit stream, pass it to the transmitter model so that we get the output of the transmitter block. We convolve it with the analog channel, which will effectively give us the waveform at the input to the RX pad, or at the RX pad. We give that to the receiver model, and then we go ahead and run that and accumulate the output. And so now we have a simulation where the effects of the transmitter and receiver equalization are both dynamic. Okay, implications? Well, this is the best possible case because it fully supports all of the features of statistical and time domain simulation. As before, we have to allow the RX feedback loops to settle because it typically takes a long time before we're accumulating data. This is one where it's valid to use statistical simulations to explore a lot of variables and then maybe pick the best cases and run them in time domain because statistical typically runs a lot faster than time domain. And what we should do, just sort of calibrate how well statistical predicts time domain, is really take a set of cases and look at both the statistical and time domain results to see how well they compare. Because in a perfect world, the statistical and time domain results will compare almost exactly. All right, so if we put all of that together, what we can do is we can draw the flow for how the simulator works in statistical and time domain analysis. And what we see is that in statistical simulation, really the flow is invariant. We take the analog channel impulse response, we give it to the transmit model, we take what comes out, give it to the receiver model, and then we feed that into the statistical engine. And that never changes. Even when things are missing, that flow never changes. In the time domain, we take the bit stream, we pass it to TX Getwave if it exists. We take, if not, we just skip that step. We take what comes out and we convolve it with something. We take that, we pass it to RX Getwave if it exists, and then we take the output of that and we put it into the time domain engine. And the only variant in this whole flow is what we feed into this convolution box, which is based on the combination of the capability of the transmit model and the receive model. Okay, and you'll notice here these 1, 2s, and 3s. What we're saying here is that these are just the signals at nodes that are representing what gets fed into this convolution box. Now, armed with that knowledge, then what we can do is that we can go and we can look at all of these cases and ask ourselves the question, when we're looking at simulation results, what do they represent? For instance, when I look at a statistical eye, does it have everything in it or not? Is it missing something? How should I think of it? When I look at a time domain result, does it have static or dynamic equalization? And so what we've done here is we've gone through and we've itemized all these things and shown good, bad, and indifferent, what all these cases represent. Right? And what we note in particular is time domain results are always valid. They always include both transmit and receive equalization, even though sometimes the equalization might only be static. The statistical results are sometimes missing behaviors that either make the, still allow the thing to be useful, like this is the signal at the RX pad, or sometimes they're just not particularly useful at all, like a signal that has receive equalization but no transmitter equalization has no correspondence to a node in the physical circuit, and therefore it's not really useful, and we don't really do much with it. Okay, and as we've already said, case 9 really represents our best possible case. All right, if we put it all together in one slide, it looks like this. And so, if you were to take this and print this and put it up on your wall, might not be a bad little thing to have there just when you're running with AMI models. All right, and then we're going to make a couple of other real quick notes. So when we look at AMI models, the receiver models actually return two things. They return the equalized signal and they return recovered clock behavior. And that's because just because you have an eye at the input of the data latch, if you don't know when you're firing the clock, you don't know whether you're achieving successful data or not. So you not only need to know that you have an eye, right, at your input to your sampling latch, you need to know when the clock is firing. And AMI models actually produce both of those outputs that the simulator then processes and uses to produce eye diagrams. That is a fairly complex set of topics that we don't have time to get into today, but I want to make the point. I also want to point out that receiver models actually don't have to return clock behavior at all, and if they don't, the simulator has to do something meaningful with the results nonetheless. And in the cases where receiver models have jitter budgets, there are particular assumptions about the points in the circuit where the jitter is being introduced, and that gets combined with the data that's coming back from the model, and then the simulator pulls all that together when it generates the eye diagrams and the other simulation results. Now, having mentioned jitter real quickly, we'll take a look at it. IBIS-6 actually provides multiple transmit and receiver jitter sources or impairments. Transmitter jitter is assumed to directly modulate the transmitter's analog output, so that when you think about jitter transfer functions, they don't exist in AMI. Any jitter that you have is directly what's at the transmitter output. RX jitter overwhelmingly affects the behavior of the recovered clock, and you also have a single parameter that allows you to modulate the signal in the voltage domain at the sampling input or the D input to the sampling latch. And so all of those things get factored in the analysis. And again, these are fairly advanced topics. These are advanced topics that we're just not going to be able to get into today. So my point here, number one, IBIS-AMI simulation, even though we tend to run the analysis and just look at the eye diagrams, we need to understand that it's really a multi-stage process that includes multiple pre and post-processing steps, that they involve a combination of circuit simulation and signal processing techniques, and that an individual algorithmic model can be one of three types, and therefore the simulators have to support 9 different combinations of transmitter and receiver. Statistical results vary by flow. Time domain results are always valid, but the type of equalization included differs by flow. And really understanding how does the simulator work and how to isolate issues when you have problems is key to using these tools successfully.